Let us discuss formation of stationary waves and composite string. Composite string is basically a string which is made up of two sections of different material wires or strings which are having different linear mass densities tied up at a common tension between two clamps, like the situation shown in figure. In this situation, if say we bring a tuning fork close to the system and it is brought in contact with any of the clamp, the frequency at which the tuning fork is oscillating, it is transferred into the string will start oscillating. But here stationary waves will be obtained only if the wavelength in the two strings is such that at the clamps nodes are obtained, as well as this joint of the two strings is also a node. Because it is quite obvious that when wave will be reflected and transmitted at the junction, we can say the amplitude in the two sides will be different. So this joint can never oscillate with two amplitude for left hand side as well as for right hand side. So it must be a node for formation of stationary waves. Say if stationary waves are formed, we can say as this string is lighter, the wave speed is higher, and for a given frequency the wavelength will also be more. Say for example some loops are obtained in it. Say P loops are obtained in this string, and on the other side as string is heavier, the wave velocity will be less. As we know, wave velocity is inversely proportional to root mu as the tension is common. So if mu is more, speed is less, and for the given frequency if speed is less, wavelength will also be less. So here also some loops are obtained. So for the formation of stationary waves, you can say the number of loops on the two sides may be different. Here if P loops are obtained and here if Q loops are obtained. We can say in this situation frequency of tuning fork will be equals to frequency of string 1 will be equals to frequency of string 2. As we have already studied, whenever a wave is propagated from one medium to another, no matter whichever times it is reflected, transmitted, absorbed, its frequency will always remain same. Now in the first string, as P loops are obtained in a length L1, we can write now the frequency of fork will be equals to pth harmonic of the string of length L1, which can be written as P by 2L1 root of T by mu1. Similarly, for second string, it is qth harmonic. It can be written as its frequency can be written as Q by 2L2 root of T by mu2. From this expression, we can find out the ratio of number of loops obtained in the string, which can be written as P by Q is equals to L1 by L2 root of mu1 by mu2. This ratio is quite useful. You just keep it in mind. And just remember, for formation of a stationary wave in a composite string, this P by Q must be obtained in such a way that it can be expressed in terms of ratio of two integers. Otherwise, stationary waves can never be obtained. This ratio will be used in several various numerical applications. We'll also see some solved examples based on the concept. Using this, you can also find out the minimum values of P and Q for which stationary waves can exist, and correspondingly we can find out fundamental frequency and higher frequencies at which resonance can be obtained in composite strings.